Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 30th, 2025, about 8 days ago. The big hook is that this paper adapts standard autoregressive large language models into a block-diffusion generator that runs up to 2.5 times faster, without hurting quality. The paper is titled Fast-dLLM v2, Efficient Block-Diffusion LLM, and as we'll see later, the results are really impressive. In short, it uses about 1 billion fine-tuning tokens, clever complementary masking, and hierarchical caches to match or beat autoregressive baselines while enabling parallel decoding. Also, the authors shared the official GitHub. You'll find Fast-dLLM v2 code with Dream and LLADA folders, ready to run inference and evaluation scripts, an interactive chat, a Gradio web demo, and requirements. There are examples: CLI flags for KV cache and parallel decoding, benchmark scripts, and step-by-step usage to reproduce speedups. On Hugging Face, Fast-dLLM v2 pages provide 1.5 billion and 7 billion parameter weights. Model cards, install notes, and simple transformers generate examples showcasing parallel blockwise decoding. So those resources showed how to run the models. Figure 1 shows the headline performance story. Figure 1 compares throughput and accuracy, showing the 7 billion version delivers about 2.5 times higher tokens per second at similar GSM 8K accuracy. GSM 8K is a math word problem benchmark, which tests reasoning beyond surface fluency. Panel A plots accuracy versus throughput, and Panel B reports throughput across batch sizes, which highlights strong scaling from batch 1 to 4. The key message is that speed rises sharply without a quality drop. Alright. Figure 2 shows how training proceeds with blockwise decoding and partial masking, so generation stays parallel, yet autoregressive. Complementary masks mean the batch carries two mirrored views, which ensures every token is supervised in both visible and hidden contexts. The model predicts each masked token from the preceding position to preserve next token behavior. Loss is applied only to masked positions. The top row illustrates blocks, the bottom strip shows the complementary view, and the right panel provides the legend. Alright, Figure 3 explains the fast inference path. The model generates in blocks, then reuses finished blocks through a cache to avoid redundant work. The left panel shows block-by-block decoding that preserves left-to-right semantics. The zoomed panel shows the active blocks split into sub-blocks, where masked tokens are refined in parallel based on confidence. Dual cache means a small sub-block buffer that stores prefix and suffix context, so updates skip recomputation. So Table 1 summarizes head-to-head benchmark scores across coding, math, knowledge, and instruction tasks. The 1.5 billion version leads its size class with an average near 45, which signals strong quality without extra data. The 7 billion model lands around 60, edging comparable autoregressive baselines because block diffusion keeps accuracy while enabling parallel decoding. Base and plus for code mean two eval plus settings, where plus applies stricter tests. The upper block lists 1 billion scale models, and the lower block lists 7 billion plus entries. While Figure 7 shows how the attention mask orchestrates training and decoding for block diffusion so tokens see the right context without breaking left-to-right semantics. An attention mask is a pattern that permits or blocks connections between positions, which tells the model where to look. The left panel depicts training with block-diagonal bidirectional views, green offset block causal links from clean history, and orange block causal flow among clean tokens. The right panel depicts inference, where earlier blocks are cached as a frozen prefix, and only the current noised block computes bidirectional updates. The legend clarifies attention computation versus cached regions. Wrapping up, two takeaways stand out. The method adapts autoregressive decoders with about 1 billion tokens, a roughly 500 times data reduction, and the block diffusion plus hierarchical caches deliver up to 2.5 times faster decoding without quality loss. The broader implication is practical, cheaper, parallel language generation at deployment scale. Thanks for listening. I am Alex, signing off.